Hello student, welcome to our lesson today. We are going to look at nuclear equations. Now, if you recall, we know that atoms are made of particles, and these particles are protons, neutrons, and electrons. Now, these particles can be written using the upper and lower subscripts. For instance, if you have a proton with a charge of +1 and a mass of 1 unit is written as P11. Then a neutron has no charge and a mass of 1 unit, therefore it is written as 10. Then an electron with a negative charge and a negligible mass is written as 0, -1. Note that the upper one is representing the mass and the lower one is representing the charge. Now, it is also important to know that the law of conservation is applied in this radioactive decay, which implies that the mass number before the decay or before the radioactive decay must be equal to the mass number after the decay. That is, the sum of protons on the left-hand side of the equation must be equal to the number of protons on the right-hand side of the equation. So it is always important to leave your equation balanced. Then from there we can move to nuclear reactions. We start with alpha decay. Now, an alpha is represented by a helium particle and denoted by a Greek letter alpha, which implies that it has a mass of 4 and a charge of +2. Now, when an alpha particle is emitted from the nucleus, it implies that both atomic number and the mass number decreases, and a new nuclide with a new composition is formed. The atomic number of the new nuclide decreases by 2, and the mass number of the new nuclide decreases by 4, and it can be represented by the following equation. So you have the mass number having 4a, and the atomic number represented by Z. So a mass number is reducing by 4. So this will be a minus 4. Then the atomic number will be Z minus 2, and then our equation must be balanced, so we have to write our alpha particle here that is emitted. So the original is called the parent nucleide, then the new nucleide, we call it daughter nucleide, and then we have an alpha particle. For instance, we can have Protactinium-233 that decays by emitting an alpha particle to become actinium-29. That one can be represented as follows. You have Practinium-233. The mass number will reduce by 4, so you get 229, then plus helium particle. So if you add 229 plus 4, you get 233. And if you add 89 plus 2, you get 91. So our equation is balanced. This equation is what we call the nuclear equation, because it is involving the nucleus of an atom, not the valency electron, but the nucleus of an atom. Then from there we can move to beta decay. Now, when a beta particle is emitted, the atomic number increases by 1 and the mass number remains constant. So this can be expressed as follows. You have X having a mass number of A and atomic number of Z. So when it releases a beta particle, which is represented by an electron, then the mass number remains by 1. The mass number remains the same, that is, and the atomic number increases by 1. So you have Z plus 1, then this is the electron. This is our parent nucleide, we have the daughter nucleide and a beta particle. Why is this one increasing by 1? We have the reasons here. Now, during the beta emission, a neutron spontaneously changes into proton. And how does it do that? It releases an electron. Remember, neutron is neutral. In other words, it carries no charge. So by giving out or by releasing an electron, it implies that it will have a deficit of a negative charge. Therefore, it becomes a proton. A proton is positively charged. By so doing, we have this as the equation. This is our neutron. It becomes proton by releasing an electron. by so doing, there is an increase of +1 in the nuclide. And that is why now we are saying the positive charge increases in the process. And that positive charge is reflected by adding 1 in the atomic number. Now, the mass of particles emitted is negligible. So we have an example here. Radioactive sodium, for instance, it undergoes better decay to become magnesium, and it can be written as this. We have sodium 24, a mass of 11, an atomic number of 11. It becomes magnesium 24 with a mass of with atomic number of 12. Note that we have just added 1 to 11 to become 12. And because our equation has to be balanced, then we have to add an electron. So again, when you add 12 plus minus 1, you get 11. So our equation is balanced. From there, we move to gamma radiations. Now, the emission of gamma rays, which is in form of energy, always accompanies other radioactive emission. Previously, we have seen that gamma rays cannot be emitted alone. And these are rays, in other words, they are electromagnetic waves. They are not particles. So when they are produced, or in other words, they are produced because the remaining particles after the radioactive decay have to reorganize themselves in order to form more stable arrangements. And by so doing, there is an emission of energy, and that energy is in form of gamma radiations. Now, gamma radiations or gamma rays are not shown when writing nuclear equations because they have no effect on mass number and atomic number of the nuclide. So when we are writing, we don't write them in the equation. So we have an example here. You have uranium-236. It emits, or it undergoes a decay to become barium-141 and krypton-92. And by so doing, it releases 3 neutrons and energy. So that is the equation. We just write it in form of energy. Then from there, we move to the assignment. The assignment is just testing what we have just learned. So make sure that you revisit, you revise, and then you come and attempt the assignment. So thank you, and let us meet in our next lesson.